All right, in this chapter, we're going to study if statements and while statements. Now, in just about every program except uh, the most simple programs you could imagine are at some point going to have to make a decision. Should it do statement A or not do statement A? Or should it do statement A or statement B? It should do one of the two. Which one should it do? So programs uh, very common operation within a computer program is to make decisions, and we use the if statement to make decisions. There are two forms of the if statement, one of which I call the if else because it uses both the reserved word if and the reserved word else. And then the other form, which I call a simple if, which uses the reserved word if, but it doesn't use the else reserved word. Now, all programs except the most simplest ones also will have segments of statements that are repeatedly executed. A sequence of statements that are repeatedly executed is called a loop. And we implement loops. We can implement loops in a variety of ways, one of which is to use the while statement. All right, so let's take a close look at these two statements, these two types of statements, the if statement and the while statement. Now, this is the format of the simple statement, simple if statement. It starts with the reserved word if and then parentheses, and inside parentheses, you have to have something that evaluates to either true or false. So it could be, for example, a relational expression or a Boolean expression. Relational expressions evaluate to true or false, and so do Boolean expressions. And then inside the if statement, typically you write it following the if statement. You have the first line of the if statement. You have another statement, and that's executed, but only if the expression evaluates to true. So if the true-false expression is true, then you execute the statement that's inside the if. If it's false, you skip over it. You don't execute it. Now notice when I've shown on this slide the statement inside the if, I've indented. Now indentation has no effect on what the compiler will do, but it does indicate to whoever is looking at the program that the statement is inside and under control of the if statement. So you don't want to put it starting in the same column as the reserved word if. You want to indent it. That gives it visual signal that it's it's inside the if statement. So the second thing on this slide is an actual example. Assume count is some sort of int variable, and it has some integer number in there. And let's assume count has the number 5. All right, then count is less than or equal to 10, right? 5 is less than or equal to 10. So that expression would evaluate to true, and therefore the statement that's inside this if, the system.out.println too few, would then be executed. So if count is, 9, 10, 9, 8, 7, 6, so on and so forth. If count has any value that's less than or equal to 10, then you're going to do too few. But let's say count is 20. Then that expression, count less than or equal to 10, is false, in which case the computer doesn't execute the print line too few. It will skip over it. All right, that's it. That's basically how the if statement. It's statements whose execution pretty much follows intuitively just from the English use of the word if. By the way, the statement that's inside an if statement can be a compound statement. And as you know, a compound statement starts with the left brace and ends with the right brace. And between those two braces, you can have any number of statements you want. So if you have a compound statement, then that whole compound statement is under control of the if. However, if you don't have a compound statement, then it's just whatever statement immediately follows that first line. That's the only statement that is under control of the if. All right, now, as I said, compiler doesn't care about indentation. So here we're in this first example here, we are indenting the statement that's inside the if, that's under control of the if. Now, the second print line statement is just a statement that follows the whole if. So that statement, the one that displays by, is always going to be executed. But the statement that's inside the first print line, the one that displays too few, will not necessarily be executed. If count is less than or equal to 10, it's executed. You'll get out too few, and then you'll get out by. But if count is greater than 10, then the too few print line will be skipped, and you'll get out just by. Now, what's going to happen with the second example here? Let's say count is 20, all right? So the true-false expression evaluates the false. Then you skip over the statement that's inside the if statement. That's below it, that is inside, it's under control of the if statement. So in that case, if it's 20, if count is 20, then you don't do anything. You don't do any print line statement. You don't display too few or by. But that's incorrect, right? Because an indentation doesn't matter. The second example is identical as far as the compiler is concerned to the first example. The if statement in the second example applies just to the following statement because it's not a compound statement. So it just applies, it just controls that statement. And then the print line that displays by is just the statement that follows the if statement. Now you can see how if you don't indent properly, you yourself, when you're looking at your code, may make incorrect assumptions about how the statement works. Very important that you indent in a way that reflects the actual structure of the program. So the first example does that. The first print line is indented to indicate it's inside, it's under control of the first if statement, And then the second print line, which displays by, starts in the same column as the if does, which indicates it's just the next statement that will be executed regardless of what the if statement does. All right, very important. Indentation is very important. If you do not indent, if you're writing a fairly complex program, you do not indent properly, you're probably going to have more bugs in your program than if you indent properly. And when you try to debug a program with improper indentation, it's very easy to miss the errors you're making because the indentation is incorrect and you think your program works one way where in fact it doesn't. Indentation is not being, let's see, what's that word? I forgot that word, where you're just, you pay attention to unimportant details, but paying attention to indentation is not an unimportant detail. It's extremely important. If you work for a company, they're going to require you to format your program in a very specific way. And in particular, they'll want proper indentation. Okay, now here's the other kind of if statement, and it gives you a choice between two statements. So if the true-false expression is true, then statement 1 will be executed. But if it's false, then statement 2 will be executed. So when you execute an if-else type of statement, one of the two statements is going to be executed depending upon the value of the true-false expression. So down in the actual code here, we have an example. If count is 5, then the true-false expression is true, so you will display too few. If, however, count is, let's say, 20, then the true-false expression is false, in which case you will display enough. And for either of those two cases, you'll get out by at the end because that print line, that last one that displays by, is just a statement that follows the if-else statement. So no matter what the if-else statement does, you're still going to, regardless, you're going to go fall through to that last print line, which displays by. So this is going to display either too few and by or enough and by. You always get by at the end because it's just the next statement that follows the whole if-else statement. Now here I'm showing the use of compound statements. We have an if statement that starts with if x is less than 50. If it is, that would mean the expression evaluates to true, in which case you're going to execute the compound statement that's under control of the if. So you'll execute the print line that displays incrementing x, and then you do x plus plus. Remember what that does? It just adds 1 to the value in x. It increases. We call that the incrementation operator because it adds 1 to the value of x. Now, if x is greater than 70, then you do the else part, which also consists of a compound statement. So in that case, you'll also do those two statements, the decrementing x and then x minus minus, which decrements x by 1. And then no matter what happens with the if-else statement, you do the print line at the end by, because it's the statement that follows the if-else statement. It's not part of the else part, and it's not part of the if part of the if-else. All right, now you can have if statements within if statements. And, you just have to be logical about the way the if statement works, and you can very easily figure out yourself what this does. So here we have an if statement, and inside there you have an if-else statement. So the if-else statement is under control of the first if. So if x is equal to 3, by the way, notice I'm using the double equal sign. You don't want to have a single equal sign because that means you're going to assign 3 to x. You want the double equal sign, which is checking for the equality of the value in x and 3. So if that's true, if x is equal to 3, then you're going to do the if-else statement. But if x equals 4, you don't do the if-else statement, which means you don't do anything, right? You just skip to whatever follows this whole nested if statement. All right, so this is one statement here, the if-else, and so it's one statement that follows an if statement. So that if-else statement is under control of the if statement. All right. By the way, there is a rule that the else associates with the nearest if. So the nearest if for the else is that second if. So that means the second if is the beginning of an if-else. The else doesn't associate with the first if. I mean, if it did, then the first if would be the if-else, and the second if would be just a simple if that's part of the if part of the outer if. Okay, I probably need to say that again. So because this thing, the else, associates with the second if, if y equals 5, then that second if is the beginning of an if-else statement, which means the first if is just a simple if statement, which happens to have inside it an if-else statement. All right, so the first if is a simple if statement, and then inside that simple if statement is a single statement, which is if-else. If, however, that else associated with the first if, which it does not, I said the rule is a else associates with the nearest if. So if it were, then the first if statement would be an if-else, and that second if would be a simple if statement. All right, so if that were the case, you would have that second if statement as the if part for the outer if, and the else statement would be the else part of the outer if. But it doesn't work that way. All right, so if it's true, then you do the statement that's inside it, which is the whole if. If it's false, you skip everything, right? Just go on to the next statement. All right, now we can change what else associates with using braces. In this example, I am putting braces around the if part of this if here. And so this whole thing here um, is a simple if. I'm forcing this whole thing here inside here to be a simple if, which means that the else has to associate with the first if, not the second if. All right, so even though this else, this is the nearest if, that second if is the nearest if, because it's inside braces, it's part of a compound statement that consists of just a single statement. Because it's inside braces, that else is forced to associate with that first if. So this is how this one's going to work. If x is 3, let's say x is not 3, then you'll display pair, right? But if x is 3, then you do the if part of that if statement, which is another if statement. So if x is 3 and x is 5, then you'll display apple. If x is 3, you're going to do the if statement inside the compound statement. If x is like 7, then you're not going to display anything. You won't display apple or pear. Let me say that again. If x is 3 and y is 7, then you don't display apple, and of course you don't display pear either, right? Because the if else will take you to its if part, which has the option of either displaying apple or not. But if y is 7, it's not going to display apple. All right, so be sure, just go over these examples until you thoroughly understand them. You don't want to not quite understand if and if else, because then when you write code, you're going to make a mistake, and it's going to be hard to debug. It's going to be pretty much impossible if you don't understand how the language works. You're going to make mistakes because you don't understand, and then to debug your program, you're going to not be able to because you have a misconception on how the Java language works. So it's very important you understand these basic features of each statement. All right, now another way to get a else to associate with the first if is to do what I've done here. So we have here an example, and we have an if-else statement inside this if-else statement. All right, so we have an if-else inside an if statement. So the rule says else associates with the nearest if. So the first else there is going to associate with the second if. All right, the first else associates with the second if. The second if is the one that has 5 is equal to y is equal to 5. That one. All right, that's the rule. And we apply that rule because we don't have compound statements forcing else to go elsewhere. All right, so that else, that first else, associates with the second if, which is if y is equal to 5. Now look at the else part. It just has a semicolon there. Now a semicolon is a null statement. So when it's executed, nothing happens. It's not translated to any executable code. The purpose of having the else semicolon is just to force that else to associate with the second if, which means that then using the rule, that second else is going to associate with the first if, because the second if already has an else associated with it. So that rule is not, I didn't state it precisely, like the second else associates with the nearest if, which does not already have an else associated with it. So that is the correct statement of the rule. So this second else doesn't associate with the second if, because that second if already has that first else associated with it. So the second else necessarily associates with the first if. All right, so let's see what happens. If x is 5, then you do the else part and you display pair. If x is 3 and y is 5, then you display apple. If x is 3 and y is 7, then you go into that if part of that first if there, and the y equals 5 is false if y is 7, so you do the else part, which does nothing, so nothing is displayed in that case. So this works like the previous example. And some people like to do this. And this is perfectly okay. I would either do this or use the compound, use the braces to create a compound statement to force the second else to associate with the first if. All right, now we can also use nested if statements to do multi-way branches. So here's an example. I want to do either statement 1, statement 2, statement 3, or statement 4, depending upon the value of x. So this is what's going to happen. If x is 5, you do statement 1, and then you're done with the whole statement, right? But if x is not 5, then you're going to do the else part. Okay, that else part is also a nested if-else statement. All right, so if x is, let's say, 7, then you're going to do the else part of that if statement, which starts at the 1, 2, 3, 4th line. It starts with if x equals 6. All right, so if x is 7, you don't do statement 1, you do what follows that first else, that whole thing there. So if x is 6, then you do statement 2, but if it's not 6, then you do the else part. All right, and so if you do the else part, if x is not 6, then you go to the else part of that inner if-else statement. And if x is 7, then you'll do statement 3. If x is neither 5 nor 6 nor 7, then you'll do statement 4. All right, so if x is 5, you do statement 1. If x is 6, you'll do statement 2. If x is 7, you'll do statement 3. And if x is something other than 5, 6, or 7, then you'll do statement 4. So this is one way of creating multi-way branches. So in effect, when you hit this statement, you're going to either kind of branch out to either statement 1, statement 2, statement 3, or statement 4. And then after doing one of those, then you'll continue with whatever follows this whole multi-way branch structure. Now, Java has another way of specifying multi-way branches that we'll talk about at some point in the future. But for now, you should know what's happening here and be able to use it if necessary. Now we get to while loop. A loop, again, is a sequence of statements that are executed repeatedly. Now, the thing you might ask immediately when I tell you that, why would you want to execute a sequence of statements immediately? If you've done it once, if you've done the sequence of statements once, isn't that enough? I mean, what good is it to just do something repeatedly? Like if you, let's see, what would be, if you need, let's say, milk, right? And you drive to the store and get milk and bring it back, so now you have milk. Why do it again? Why do it again? Bring back another container and then do it again. Do it like 1,000 times, so you have 1,000 containers of milk in your house. You would think just doing something once would be enough. But here's why loops are very important, are very useful, very important, and make sense. Each time you execute a loop, a sequence of statements, which makes up a loop, that sequence of statements with no changes, can use different data. So even though you're executing the same exact sequence of statements, they're operating on different data each time. So you're actually doing a different computation each time you execute the body of a loop. All right, so in fact, and we'll see examples of that coming up. So in fact, a loop can be a very useful thing. The great thing about a loop is to type in, let's say, a five statement loop, doesn't take much time. You might be, if you're a good typist, you could type it in a minute. Then you compile the program and run it. That loop, you might have it set up so it it executes, a billion times. Modern computers can easily execute a 5-statement loop a billion times in very short period of time. So you can actually perform like 5 million statements, which involves some sort of computation. 5 million of them, or 5 billion if the loop executes 5 billion times, which does an enormous amount of computation. But in order to create the program, it took only a minute. Now, if you don't have the ability to execute loops, then if you want to, have whatever the computing device execute 5 billion computations, you're going to have to enter 5 billion instructions, which obviously is not reasonable. It's going to take a long time. But with a loop, you just repeatedly execute the same sequence of statements, each time with different data. You can do huge amount of computation in a very short period of time. And the time takes to write such a program is just like a minute or so. All right, so anyway, here's the format of a while. It starts with the reserved word while, parentheses, which contains a true-false expression. And then inside that while loop, you have the statement that's repeatedly executed. And while loop can consist of just a single statement. Now, a statement can also be a compound statement. So let's say you want to, and that's typically the case. While loops and all loops generally will be, maybe 5, 10, maybe 20 statements inside a compound, inside the braces, which makes that whole thing a compound statement. All right, so let's take some examples. Here is the action of a while loop. So you come into the while loop from above, from the statement preceding the while loop, and the first thing that computer does when it starts the execution of a while loop is it evaluates the true-false expression. All right, so right at the beginning. Now I call that the exit test because it may trigger the exit from the loop. If that true-false expression evaluates the false, then the computer will jump out of the loop and proceed to the next statement that follows the whole while loop structure. All right, so I call that an exit test, and the exit test is right at the beginning of the loop. The very first thing that is done is evaluate the true-false expression, which is the exit test. So I describe this situation by saying that the while loop has a leading exit test. Leading means right at the beginning. All right, so if the expression, let's say, is true initially, then you execute the body of the loop, what's inside, the loop. And then after you do that, you go back up to the point where you evaluate the expression. You evaluate it again. And if it's still true, then you do the loop body again. Then you go back up and reevaluate the true-false expression. As long as that true-false expression is true, it just keeps repeatedly executing the body of the loop, which could be a single statement, could be 20 statements in the form of a compound statement. Now, hopefully, eventually, that true-false statement will go false, which causes an exit from the loop, and the computer then proceeds to the next statement that follows the whole while loop structure. Now, if that doesn't happen, then you have something which is not a very good situation. You have what's called an infinite bug. It's just the computer is just going to stay in that loop forever. Now, of course, it's not going to do that because at some point, you'll turn off the computer, or you will force your program to halt. Typically, that's what happens. You force the program to halt. And the way to do that is to do Control-Z or Control-Z or Control-C. One of those should work depending on your system. Hold down the Control key and hit Z, or you hold down the Control key and hit D, or one of those. I think the textbook indicates. It depends on the system. All right, so So if you run a program, now on most computers these days, the programs you're going to write should execute almost instantly. So a second later, it should finish. If it doesn't finish right away, that means one of two things. You got an infinite loop, and you can sit there all day. It's not going to finish. Or it's waiting, your program, you've programmed a statement in your computer that we haven't studied yet, and it's waiting for you to enter some data on the keyboard. So it's just waiting for you. And so it will wait indefinitely until you type in the data it needs. Then it will continue again. So that's not really an infinite loop. That's just the pause that occurs when the program wants some data via the keyboard from whoever is running the program. All right, so to review, while loop has a leading exit test. So it's possible the body of the loop will not be executed at all, right? If that true false expression, the very first time you enter that while loop, if that true false expression is false, then you don't execute the body of the loop at all. All right. All right, now here's an actual example of a loop. And this is example of what I call a count control loop, because the exit depends on a count. Now, if you look at line 5, I'm initializing count to 1. And then if you look at line 10, which is the end of the body of the loop, I'm incrementing count by 1. So each time the body of the loop executes, count is increased. It's initially 1, and then in line 10, it gets increased to 2. And then when count is 2, line 6 is still true, right? 2 is less than or equal to 3. So again, you execute the body of loop, but on line 10, it then gets incremented to 3. And then on line 6, 3 is less than or equal to 3, so it's still true. So you go through the body of the loop a third time, and on line 10, you again increment count to 4. But now when you go back up to 6, that relational expression is false. 4 is not less than or equal to 3. So at that point, you exit from the loop. So for this particular example, the body of the loop, lines 8, 9, and 10 are executed exactly 3 times. When count is 1, count is 2, count is 3. When count goes up to 4, the exit occurs. You don't proceed into statement 8 and then 9 and then 10 again. All right, so it just makes sense to call it a count control loop, because the count is keeping track of the number of times the loop executes, and when it reaches the appropriate number, or when it exceeds it by 1, then that triggers the exit from the loop. So what is going to be displayed by this program? We're going to get star moon, star moon, star moon. 3 times star moon will be displayed. And then the exit occurs when count is 4. And then you get good night. Star moon, star moon, star moon, and then good night. Some of you may be familiar with a book, very famous book, called Good Night Moon. And I think I was thinking of that book. It's for little kids, but it's a great book. You know, if you have a little kid, you definitely want to get that book, Good Night Moon. All right. Let's go on to a variation here. I am creating a loop that also executes exactly 3 times, except we're counting down from 3 to 1. So count is initially 3, so count is greater than or equal to 1, so we're going to execute the body. Then count goes down to 2, which means the relational expression is still true. And so we execute the body of the loop a second time. By the way, the body of the loop is represented by those 3 dots. I'm just not showing you what's inside the loop. And then count goes down to 1. And the relational expression is still true, right? Because 1 is greater than or equal to 1. But then count goes down to 0. And then when you go back up to the exit test, the count greater than or equal 0 is not greater than or equal to 1. So therefore, when you finally count down to 0, you exit the loop. So this loop is going to execute for count equals 3, count equals 2, count equals 1, and then when count reaches 0, you get the exit, so it doesn't execute it for count equals 0. So it executes just like the previous example 3 times, but count is being decremented each time. We're counting down until the count goes below 0, and then we exit, rather than counting up. So sometimes you might want to use a count down kind of count control loop or a count up count control loop. All right, now here's another example of count control loop, and this actually does something, does do a specific computation. Now on line 5, I am initializing count to 1, and then on line 10, which is inside the body of the while loop, I'm incrementing count. Each time I do 10, I increment count. So this while loop is going to the body is going to be executed for count equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But then when count gets up to 11, then the relational expression on line 7 is going to go false, and then you quit. All right, so that loop is going to go 10 times. The body of the loop will be executed 10 times. First time the loop is executed, count is 1. Second time the loop is executed, count is 2, and so on and so forth. Last time the body of the loop is executed, count, the variable count, will contain 10. So what actually is this loop doing? Well, the very first time line 9 is executing, it's getting the value in sum and the value in count, adding the two together, and adding and assigning that sum into the variable sum on the left. So sum initially has 0, right? So the very first time I execute statement 9, the computer is going to get 0 out of sum, the variable sum. It's going to get 1 out of the count variable. Add those two together, 0 plus 1 is 1, and then assign 1 to sum. So the effect of line 9 is to add whatever is in count to increase sum by whatever is in count. Since 1 is in count, it increases sum from 0 to 1. Now the second time through the loop, we're going to execute the same statement, 9, but count on the second time is 2. So we're going to take the 1 out of sum, the 2 out of count, add the 2 together, you get 3, and put that value in sum. All right. And then the next time count is greater. It's the next one. And each time we do that, we're adding the next bigger number to sum. We're increasing sum. So we increase sum by 1, then we increase sum by 2, we increase sum by 3, increase sum by 4. We keep that up until we increase sum by 11. Then count goes up to, we increase it by 10, excuse me, that's the last one. Then count goes up to 11. And at that point, we exit the loop. So since sum starts from 0, we add 1 to sum, then we add 2 to sum, 3 to sum. We're just adding up the sum of the first 10 integers, 1 through 10. All right? And then after that while loop, we display that final sum, which is going to be 55, by the way. So line 12 will display the label sum space, S-U-M, space equals space, and then after that space, you have the value of sum, which is going to be 55. So you'll get out SUM space equals space 55. That will come out by line 12. All right, by the way, whenever you write a program and you display some answer, you should display it with a label indicating what it is. So on line 12 here, we're putting a label. We're not just displaying 55. We're saying sum equals 55. And, if you are sloppy with your labels, you misspell it. Gives an awful impression. So you want to make sure your labels are nicely, appropriately spaced. Like I like putting an a space on either side of the equal sign. I think it looks more professional rather than just jam sum, equal, and 55 all together with no embedded spaces. So make sure it's laid out nicely and you got correct spelling. So you got two important rules you always want to indent in a way that reflects the structure of the code. By the way, I'm using code to refer, it's a generic term that indicates the actual programs, the actual instructions that you're writing. You always want to indent properly, and you always want to label your output. Okay. All right, and everything should be pretty understandable. We call this count control 2. That's the name of this class. And we got our standard main header, the header there, public static void main. Remember, please send voicemail, and then string array args inside parentheses. And we're declaring count and sum, then we're doing a computation, then we display a result. So obviously that's what you do. You normally do your initialization before the loop, then the loop performs some sort of computation, and then after the loop finishes, then you want to display the final sum. Now, if you put line 12 inside the loop, that means you're going to be displaying the sum as it's being computed. So you're going to get out the first time through it. You're going to get out 1, 2, 3. You're going to get out 1, and then 3, and then 6. You're going to get out as all the values sum assumes as you're doing the computation. Normally, you wouldn't want that. You just want the final sum. So you display the result of the computation after the loop. All right. So initialization first, then the loop, then after the loop you display your results. And that's what this slide is all about. Initialization first, loop to do a computation, and then after the loop finishes, you use the result computed by the loop. It might mean just displaying it, or it might mean using it for some additional computations that still have to be done. All right, now, so we've been talking about count control loops, but there's a second kind of loop, which I call condition control. And the reason why it's called a condition control is because the exit depends on a condition. So if you look at line 7 here, we're not using a counter and counting up to a certain value or down to a certain value. We're just checking to see if some condition is true. And if it is, we do the body of the loop. If it isn't, then we exit the loop. So what we're doing here is what this program does, by the way, it displays all the square numbers, all the squares of 1 through, displaying all the squares up to that are less than 500, all the squares that are less than 500. So it's going to display 1, it's going to display 4, and then it's going to display 9, 3 squared. Then it's going to display 16. It's going to display all those squares until you reach 5,000. Then it won't display anymore. So I don't know how many I don't know what square is going to, at what point are we going to exceed 5,000 when we're looking at all the squares. So I just create a condition control loop. So on line 7, I'm actually computing the square. If it's less than 5,000, then I want to display it. And line 8 displays it. Then I increase x by 1. And then I go back to line 7 and I again evaluate. But now I'm going to, x is 1 more than the previous time. So I compute the next square, check to see if it's less than 5,000. If it is, I display it, and I keep doing that. At some point, x squared is going to be equal to or greater than 5,000, at which point I exit the loop. I don't display any more squares. All right, so that's how this one works. Now, let me just make some comments about this program. Let's see, on line 9, on line 7, notice I am squaring x by saying x asterisk x, right? You got to use asterisk to indicate multiplication. All right. And I'm using that also on line 9. Line 7 and line 9 has the expression x asterisk x, which means x times x. All right, and let's see what line 9 does. It displays the value of x. So let's say x is 2. When x is 2 and you're going through this thing, All right, so it's going to display 2, and then it's going to display space SQUARED space equals space, and then it's going to display 2 squared, which is 4. All right, so you'll get 2 squared equals 4. All right, that's what, and the plus signs there, all the plus signs don't mean, none of them mean the 2, well, there are only 2, don't mean addition, they mean concatenation, right? Because the first plus sign has a string on the right side, so the plus is going to be concatenation. And then the second plus sign is going to have the string, the squared string that says squared equals on the left, so that plus sign is going to be concatenation as well. So you'll get 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, all the way up to whatever square is, the highest square that is less than 5,000. Now, one thing I don't really particularly care about this program is that, in this case, the computation, computing square is a trivial operation, shouldn't take much time. But let's say, the exit test involves some sort of very complex, time-consuming operation. We are doing it twice. We're doing it in the exit test, and we're also doing it on line 9. So we're doing the computation twice. So that's inefficient. Normally you wouldn't want to do the computation twice. So there's another way of restructuring this program so that you do it only once. Now, if you forget about Java for a second, let's say you just want to conceptually think of a sequence of instructions that will do this. All right, so this is the way I would structure the loop. This is just sort of the natural way of structuring a loop, and then I'll show you the code that corresponds to this natural way. So it has 2 advantages, this new approach. One, you're not going to compute x squared twice. And secondly, it's the natural way, I think the most logical natural way to implement this kind of loop, which means that it should be easier to write, easier to understand. Okay, so I would do my initialization like here. X is initialized to 1. And then I would go inside the loop. And the first thing inside the loop, I would compute x squared. That would be the first thing I do inside the loop. And I would assign it to some variable. Let's call it S. All right? So that's the first thing I would do inside the loop. Okay? Before the loop, I initialize x. Then the very first thing I do, I don't do an exit test. Like this thing here is doing an exit test right at the beginning here. No exit test. The very first thing I'm going to do inside the loop is just compute the square of x, whatever it is. First time through the loop, it's going to be 1, of course, 1 squared. So first thing I do inside the loop is compute the square of x and save it. Assign it to a variable like y. All right. Then I would check to see if y, the saved value, is less than, or let me do it this way. I would check to see if y is greater than or equal to 5,000, in which case I would force immediate exit from the loop. And then if the exit didn't occur, that means the square y, which is in y, is less than 5,000, so I want to display it, so I would display y. I don't recompute x squared. I got it saved in y, so I would just display y. All right? And then I would increase x at the bottom of the loop, and then I start that whole process again. Now, the thing that's very significant to notice, that the first thing I do is not an exit test in this approach. The exit test is sort of like in the middle of the loop. And that's why the while doesn't really fit that well, because the while loop has a initial exit test. You want the exit test to be in the middle of the loop. The first thing you want the body of the loop to do is compute x squared. Then you do the exit test. You don't do the exit test right at the beginning. All right, so let's see how this new approach would look in code. Oh, by the way, this is what this program is going to do. It's going to say 1 squared equals 1, 2 squared equals 4, and so on and so forth, all the way up to 70 squared. When you get to 71 squared, the value is going to be more than 5,000. It's going to be greater than or equal to 5,000. So the loop executes when you get up to 70. So here is the structure, this new structure that I think is the logical structure. First thing you do is compute x squared and save it in a variable. I'm using square here. All right. Then after you do that, you do your exit test. All right. And you don't recompute the square because you saved it in square. All right. So the exit test is not at the very beginning. It's in the middle, not quite, but it's it's in the interior of the body of the loop. All right, so if square is greater than or equal to 5,000, then you're done, right? And you want to exit immediately. But if it's not, then you want to square that, display it, not square it, display it, and then you increment x and start that process again. All right, so this has an interior exit test. This is the natural way of doing this loop. By the way, when you're writing a program that requires a loop, I would, before you write code, try to just sort of map out what the structure of the loop is going to be. And if the exit test just naturally falls, the exit test naturally falls in the interior, it's not at the very beginning, then use this new form that I'm about to show you. All right? Use this new form. Use the form that corresponds to this kind of structure where you have an interior exit test. All right, so here we have it, and here's the new form. So I'm still going to use the keyword while, if you notice line 7, but the inside parentheses I'm going to use the Boolean constant true, which of course always evaluates to true. It's the constant true, so it always evaluates to true. All right, and then on line 9, this is the very beginning of the body of your loop. I compute the square of x, and I assign it to the variable square. And then on line 10, I check to see if square is greater than or equal to 500. If it is, I execute a new statement. You haven't seen it before, break. And the effect of that is to break out of the while loop. So in this case, you break out of the while loop and nothing follows the while loop. So at that point, the program would end. All right. But if square is less than 5,000, then you go on to line 11 and display, whatever, like 1 squared equals 1, or on the next iteration, it would be 2 squared equals 4, and so on and so forth. And then on line 12, you increase x by 1. All right, so this is the way. Now, there are some purists out there who don't like this approach. And the reason why is because you have to look inside the loop to determine what the exit test is. What determines an exit from the loop? Whereas if you have a exit test right at the beginning, which is unnatural for this particular problem, then you know immediately by looking at the first line. However, in practice, I don't think that's a real liability to do this approach, and it's the natural approach. So I approve of this, and I suggest you use this approach. Whenever you have an exit test that naturally falls in the interior of the loop, use this structure. You use an if statement to do the exit test, and the break statement to break out of the loop if the exit test evaluates to true. All right. Now, those purists, and there are some out there, you might have a professor who's a purist, want you to use this approach, which seems to me really idiotic, but there will be some who think this is the way to do it. So what we're doing in this approach it's not a fake while loop, it's an actual fake while loop. On line 8, you have keep going, which is a Boolean, which is initially true, and eventually it will go false. So if you look at line 8, you know that whenever keep going goes false, that's going to cause the exit of the loop. You don't have to look inside to know that keep going is the key thing. But in order to know where the exit test, where the exit is going to occur, you got to look inside the loop to see where keep going will be ultimately assigned to false. So if you look at, we do the square first, right? So the very first thing inside the loop, we're computing square on line 10 and assigning it to square. Then we're checking to see if we want to get out of this loop. So instead of just doing a break, we set keep going to false. So the next time we go up to line 8, keep going is false, so we exit out of the loop. So it just seems like a roundabout way of doing doing what the previous example does, but in a much more complicated way. You know, you're basically triggering the exit. It's sort of the same structure. You know, the first thing you do inside the loop is square X and save it. Then you have your exit test. But instead of just simply breaking out of there, you do this weird thing, keep going, assign it to false, which then means that you then will exit when you go back up to line 8. Now, if the exit test is false, so you don't want to break out of the loop, then you do the else part. You display the square, then you increment X. So I don't like this. If you want to do this just to get experience at doing something like this, it's okay. But I think it's just sort of you know the word I was looking before, the one where you're being very picky in a very unreasonable way. You're not doing anything constructive. The word is pedantic. So I think someone who says this is the way you have to do it, he's being pedantic. The other way is better. It's the natural way. It's the more efficient way. It will execute more quickly. The code will be shorter in length. So I think anybody who pushes this is just being sort of like crazy purists who insists that, you know, the while loop, you know, at the very beginning of the while loop, you have to do the exit test. You can't have while true like in the previous example. All right, now here's another approach, and this is sometimes used. This is not a bad approach. What we're doing here on line 7 is computing the square. Then we have the exit test. So before we enter the loop, we do our first square. So so in effect, the exit test is in the middle of the repetition. We're going to do line 7, right? We're going to do the square. Then we have the exit test. Then we do the print line, displays the square. Then we increment X. Then we do the square again, except we do that on line 12 and not on line 7. So this logically is doing the square in the middle of the loop if you count line 7, the beginning of the loop. See, if you consider line 7, the beginning of the loop, you're doing the square, right? The exit test, the print line, if it passes the exit test, increment, and then you start the procedure over again. You do the square, then you do the exit test, and then you do the print line, and then you increment X. Then you start the loop again, square, then the exit test, then the print line, then X squared. So by doing this, you in effect are using the while loop the way it normally is used. You have a valid exit test, but the effect is to have the exit test, that while loop, in the middle of the loop and not in the middle of the loop, even though you know, you're using a normal while loop there. That's the effect. And line 7 is called the priming statement. You know, it sort of primes the thing, and then you get inside the while loop. Now, are we doing the computation twice? No. Each time through the loop, we're going to do it just once. So for x equals 1, we do it once on line 7, and then we do line 8, line 9, 10, 11, and then 12. We do the next. We're not doing x on line on line 11 is incremented. So on line 12, we're not doing the computation again. The same computation, x is incremented, and so and at that point on, we just stay within the while loop. So each time through, we're just doing it once. So we're not doing repetitive. We're not doing the same computation a second time like in the very first example. All right, so this is a nice way of doing it. However, I still like the approach where you use the break statement and you have while true at the beginning and you use the break statement. By the way, I think some cultures sometimes grow up around the language. And I think the people who are, like Java aficionados have a certain culture. They're sort of tend to be more on the purist side. Things have to be done just a certain way. But uh, the people who are really are aficionados of Python, another programming language, which is a very nice one, they're more, sort of a little more flexible. So I noticed that when I'm looking at, books that talk about Python, that explain Python, they use the approach I like with the break statement. And I think that just reflects their culture as not being quite as pedantic as people who are really into Java. Although, like I'm into Java and I don't feel I'm pedantic. So I wouldn't make a blanket statement about everybody who's into Java. But I do think there is a little bit. One other thing I already mentioned, people in Java, they refer to a pointer, a thing that's pointing to an object. They don't want to use pointer. They use reference. It's a reference variable. They don't say pointer variable. I think pointer just makes sense because it describes the you just get a sense of what it is. It's a pointer that's pointing to an object. But they don't want to call pointer because for various reasons I don't want to go into here. But I understand why but I think it's better to just call it a pointer. It just makes more sense because it's more understandable. All right. All right, now let's write a program that involves keyboard input. Now, when we run this program, the first thing it does is it outputs a prompt statement. Now, a prompt statement tells the user that keyboard input is requested. And after it generates this prompt message, it's going to wait for the user at the keyboard to enter something, right? So you get out this message. If you run this program I'm about to show you, you get out the message, enter integer greater than 0. And then the computer is going to stop, wait for you to type in some number. You could wait there for an hour, nothing's going to happen because the computer is waiting. It's pausing for you to enter a integer number. So when you finally enter 10, then it will proceed and compute the sum of the integers 1 to 10, which is 55. Now, if you run the program a second time, you'll get the same prompt message. And if this time you enter 20, you'll get the sum of the integers 1 to 20, which happens to be equal to 210. Now, a very bad mistake is to do keyboard input but not precede the statement that does the input with the prompt message, because you run the program, nothing happens, you don't see the prompt message, so you're just sitting there, nothing's happening. And you might think, gee, it must be an infinite loop, where in fact it's not an infinite loop, it's just waiting for keyboard input. So it's very important that you always precede keyboard input statement with a prompt message. All right, so let's see. Always indent properly, always label your output meaningfully, like sum equals or average equals, current temperature equals, whatever. Always precede keyboard input with the appropriate prompt statement that tells the user exactly what's required. All right. All right, so here is the program that does that. By the way, this is a more versatile program than the ones we've been looking at, because the ones we've been looking at will perform a specific sum. Like if you have the exit test up to 10, right? It will determine the sum of the numbers from 1 to 10. Or you can change it. If you change the program and recompile it, then let's say you change it so it will go all the way up to 20. Then it will determine the sum of the integers from 1 to 20. But it will only do it for one particular case. This one will work for any case. You could type in 10, run it again without changing the program. You enter 20, it will sum up all the integers from 1 to 20 and so on and so forth. So it's a more versatile program. So that's a nice thing about it. You know, we're asking the user how many of the integers starting from 1 do you want to add up, and the user types in that number 10. So it's going to add up the integers 1 through 10. If you type in 20, then it will add up the integers 1 through 20. All right, now the first thing we have to do is create the object that will handle the keyboard input. Now, input and output, the actual input and output is a very complex thing because it involves timing. It involves a lot of sophisticated stuff. So it's nice that we can create an object that will do everything for us. So we don't really have to know anything about how the input is actually occurring. We just invoke the appropriate method in a scanner object. Now, a scanner object doesn't exist. We have to create one, and we do this on line 9. We use the new operator, and scanner is the name of the class, and it's essentially a blueprint of the object we want to create. So you say new scanner, and then inside we have something, we have system.in. System.in represents the keyboard. It has already set up to represent the keyboard. Now you can create a scanner object that's going to read in a file on your hard disk, in which case you wouldn't use system.in. We'll learn how to do that at some point later on in the course. But we want to read in from the keyboard, so you just say system.in. All right, so the result of the right-hand side of the assignment statement on line 9 is to create a new scanner object, which is initialized to work with the keyboard specified by system.in. And that new operator will return a pointer to that new object, and that pointer will be placed in KB. So KB is a variable that will point to this scanner object. All right, so we now have this scanner object that we can use to input from the keyboard. Now, line 12 is the prompt message. So on line 12, I'm prompting enter integer greater than 0, right? That's very important. By the way, if you see these lines that are in green, although when you're typing it in, you would not have different colors. Text files don't support colors, and if you're using something that does have colors, that support colors, it might not work. The compiler might not work with it. So anyway, I just colored that to make them stand out, and those are called comments. If you have a line starting with 2 slashes, then that whole line will be ignored by the compiler. So it will compile the program as if all those comment lines are not there. You could also put if you look at line 20 and 21, you could put the comment to the right of an actual statement. So the compiler will will process sum equals sum plus count, but then when it hits, the compiler hits that double slash, which starts the comment add count to sum, it will ignore that. If you didn't have the double slash there, it's going to try to translate that, and that's not valid Java code, so you would get an error message. So if you do want to have comments, you got to have that double slash preceding it. All right, so we have line 9 creates our scanner object that's going to read from the keyboard, and then line 12 is my very important prompt message. Then line 15 is what actually reads in from the keyboard. Now remember, KB is pointing to the scanner object. That scanner object has a bunch of methods. One of those methods is nextInt. Look at line 15. You see nextInt there? That's a method. and I'm invoking next in. Now you can't just say next in. You can't just say n is assigned next in. You have to indicate uh, which object, the next int in which object. So that's why we have kb.nextInt. So line 15 is going to invoke, is going to cause to execute the nextInt method in the object to which kb is pointing. All right? You have to have the kb there to indicate the object. The object itself doesn't have a name, so you use kb in effect, in lieu of the name. So kb.nextInt. Now when you execute that, the computer is going to stop. It's not going to do anything until you type in an integer. When you type in an integer, this is what's going to happen. Let's say you type in 10. Now you're typing in a decimal number. It's going to convert that to binary, and that binary number is going to be returned by the nextInt method. Remember when I said main at the very beginning? I said main, the return type is void, and that means it doesn't return anything. Well, nextInt does return something. It enters the binary equivalent of the decimal number you type in on the keyboard. And it returns it, which means the value you type in 10, that value, in effect replaces the whole right-hand side of line 15. And since this is an assignment statement, that 10 then will be assigned to n. All right, so that's it. When you execute line 15, line 9, we're creating the scanner object. Then in line 15, we're invoking the nextInt method in the scanner object to which kb points. It's going to return whatever the user enters, the integer number in binary form. It's going to convert it to binary. And then, since it returns that value, and this is an assignment statement, that value, whatever it is, 10 for example, is assigned to n. Okay, and then we go into this while loop. That is a count control loop. It's going to start from 1. Notice on line 6, we're initializing count to 1. And it's going to count all the way up to n. Well, what's n? N is the number that the user typed in. So if you type in 10, 10 will be an n. It's going to do that loop for n equals 1, 2, 3, 4, all the way up to 10. So you're going to sum up the line 20 thing is going to just add, starting from 0, sum equals 0, it's going to add all the numbers 1 through 10. And then when you fall out of the loop, you display, let's take a look at line 24. Sum of 1, 2, right? It's going to display that. And then you have concatenation with n, but you're going to get out the value of n. So if you typed in 10 in response to line 15, you're going to get out sum of 1 to 10 equals whatever the sum is, 55. All right, so you're going to have concatenation there. You're not summing anything. You have concatenation because for each of those plus signs, we actually have, we have 3 of them, right? Yeah, you got 3 of them. Each one of those plus signs, on at least one side, you have a string, so the plus means concatenation. All right, and when you have n, without quotes around it, you're going to get whatever the current value of n is. So on line 24, you're going to get out the sum of 1 to 10, if 10 was the number you entered. And in place of sum, you're going to get out the final value that's in sum. All right, so this is a nice program. It does something actually useful. Now, if you've had, a little mathematics, you may know that there's a nice, easy formula for computing the sum of the first n positive integers. For example, if you want to determine the sum of the integers 1 from 10, that's equal to 10 times 1 more than 10, which is 11. 10 times 11 divided by 2. So 10 times 11 divided by 2, divide 2 into 10, that gives you 5. So the answer is 5 times 11, which is 55. So it's a very easy sum. If you really needed to know what that value is, you wouldn't use a loop. You would use that formula, because using that formula just involves, 1 multiplication, 1 division, and it's going to take a lot less time than this while loop. All right, so that formula is n times n plus 1 divided by that whole thing divided by 2. And that's called Gauss's formula because apparently when he was a little kid, his teacher said kept the class wanted to keep the class busy, so said, "Hey, let's add up all the positive integers from 1 to 100." And he did it right away because he somehow on his own figured out this formula, and so he, instead of taking a half hour to do the compute, he just amazed his teacher by knowing the answer almost immediately. Gauss, by the way, was, is considered one of the greatest mathematicians ever to live.